So now let me continue with the next topic of the day, and that is arbitrage theory. So let me define arbitrage definition. Arbitrage is a strategy to make risk-free or riskless profits. So in simple words, I buy an asset and I sell an asset, and just by buying and selling the same asset at different places, I make a profit. For instance, I buy in Stuttgart, Microsoft, I sell it in Frankfurt, and due to the price difference, because I buy it at, let's say, 99 euros in Stuttgart and sell it at 100 in Frankfurt, I make €1 profit. And I do this immediately, so there's no time, and therefore there's no risk. So that is what we call arbitrage, if there's a price difference. But if this would exist, well, not only I would do this, you also, right? So everyone would buy it in Stuttgart and sell it in Frankfurt. Buy it at 99, sell it at 100. But if everyone is buying this stock in Stuttgart at 99, obviously the price would increase because there's so many demand in Stuttgart on this stock. And if everyone would sell it in Frankfurt, the price would decline in Frankfurt, supply and demand. And then immediately, the price in Stuttgart and in Frankfurt should stay at the same level. And due to the fact, that is what we see in financial market. In financial market, we always have no arbitrage. This arbitrage does not exist, and if it exists, it's immediately gone, because investors see this, buy and sell, and then it's gone. And today, it's not even investors who do these arbitrage, they are computer algorithms who screen the markets and look for certain price differences at different locations, and whenever they see one, they immediately order in milliseconds, buy here, sell here, and the price equals out. So what we can say is, in financial markets, we have what we call no arbitrage. Right? If there is arbitrage, then we would use this possibility, this opportunity, to make a risk-free profit. And due to the fact that this can stay forever, because everyone would use this, and then due to supply and demand, the price would adjust. Where there's a demand, the price would go up. Where there's too much sell, then the price would go down. Then they equal, the price would come together at these different places. So the key assumption, a central assumption, is the financial markets, we have what we call no arbitrage, or arbitrage-free markets. So what does this require, this arbitrage or arbitrage-free markets? Well, this requires that the markets are always liquid, that we can sell and buy at every place and at every time. There's no limitation. There are no transaction costs, so it does not cost anything to buy and sell. Yeah, in reality, obviously, it costs some little amount, but if it does not cost anything and there are no limitations, then it always will happen that markets are arbitrage-free, or there's no arbitrage. And we assume here, for simplification also, there's an underlying, and the underlying asset, there is no dividend payment, it's just the price of the underlying we take care, and we can sell it then and buy it. So these are the three assumptions of arbitrage-free markets, you can say. So why is this idea of arbitrage important? Well, the whole pricing, what we will do in the second part of this class, pricing a financial derivative, a call option or a put option, is based on the idea of arbitrage-free markets. If this is not true. If we have no arbitrage-free market, prices is very complex and basically it's impossible. So the whole pricing needs this assumption of arbitrage-free markets. And therefore, in the next couple of minutes, I will talk a little bit about this idea of arbitrage-free and what does arbitrage mean in general, and what are the implications of arbitrage or no arbitrage. So first of all, you can imagine that the idea of no arbitrage is a very special situation. And by the way, this was first discovered by Eugene Fama. He wrote a paper in 1973. And this is an empirical paper based on financial market data. And what he finds by this in this study is the following. By the way, in this paper, he developed a new methodology, which is called event study technique, which is now very famous. And due to this research, started here in the 70s, over the past, it really established a new field of research, and lots of researcher, famous people worked on these or related topics. Fama, together with Hansen and Shiller, got the Nobel Prize for this research in 2013. So what was the finding Eugene Fama discovered? Well, he basically found the fact, what he labeled the efficiency, market efficiency, or the efficiency hypothesis. He stated that markets are always efficient. And that means, in other words, if there's any price difference, it would be eliminated within milliseconds. Yeah? So if there is arbitrage, there are always traders screening the markets and then selling and buying, and by this, it levels out immediately, and therefore, the efficient market hypothesis is a synonym to the assumption of, in finance, to say there is no arbitrage. And he found this by looking to company stocks, and he screened thousands of companies, and then he looked to certain announcement. When company announced, well, we have a new technique, and therefore we have better profits in future, and then he screened what was the stock market before this announcement, and what is the stock price after the announcement. And what he found, well, when there's an announcement, the market jumped immediately to the new level. Before it was almost the same, afterwards it was almost the same. So with the announcement, the information was immediately priced in the market, because the investors were reacting immediately, and then it's priced in, and then nothing changes. No arbitrage. Yeah? If it would continuously go up, the price, then you would say, well, people are using this, and it levels out. But what he finds, the markets are so efficient that all mispricing is gone by a millisecond. There's an announcement, and then the price is already at the new level. And that is what he finds. And all the research after him proved this. It's consistent. So it seems to be, that is, though he developed this idea of the market efficiency, that markets are efficient. Interestingly, this is true in the short run. In the longer run, it's a little bit different. And Shiller, who also, so Robert Shiller, who is also one of the Nobel laureates, together with Fama, he always questioned this idea of efficient markets. And therefore he developed, he's one of the guys who is in the field of behavioral economics. He said, well, in the long run we see some deviation, and he explains the deviation by behavioral phenomena. Yeah? But in the short run, it seems to be still that even Shiller, who would oppose this in general, this efficient market hypothesis, but in the short run they probably say, yeah, that's true, but in the long run we can also identify certain differences. So in the end, this is the central assumption, no arbitrage. There's a bigger group of this idea of no arbitrage, and if we have no arbitrage, that is also means there is no dominant strategy. dominant strategy. But interestingly, we find cases where we can find a dominant strategy, but it does not necessarily imply that the market has no arbitrage. And there's a bigger group we can also find, and that is what we call in economics the law of one price. That means for a product there is just one particular price, PI. If there is no arbitrage, right, then for a stock Microsoft, the price at every place in the world should be the same. Law of one price. Yeah, if this is true, this is true. If we have no arbitrage, there is no dominant strategy. But interestingly, we can find cases there's a violation of no arbitrage, but the law of one price is true. So let me explain this in more detail. What does a dominant strategy mean? Dominant strategy. Well, it goes back to micro game theory. Probably you have learned something about dominant strategy. Suppose we have two investments, investment opportunity A at time 0, yeah, and we have an investment B also in 0. And we assume that the value, the price of this investment is the same today. So we can buy an asset, a stock, and the price is the same. And a dominant strategy then would imply that in period 1, in period 1, we have once again a certain value from this asset, and in period 1 we also have a value of this asset B, but then one of these is bigger. For instance, let's assume B. So we start with the same initial investment, but in the end, always B gives me a higher rate of return. Then we would say B is a dominant strategy. Well, if this is the case, everyone would invest in B and not in A, right? And we would construct a violation to no arbitrage. Because in arbitrage, this can't happen. At some point, the prices must, if we start with the same, it should be something similar than in future, if both are risky assets with the same underlying structure. And this goes not just in this direction, it goes also in the other direction. So if we assume the value of this asset is the same in period 1, so the payoff today is the same, but maybe it's different in this period. Well, suppose this is always negative, and in period 1 we always obtain a positive output. Well, then we would always do option B. Yeah, negative means I give you money and B, the investment B, and then you have the money and a positive output in period 1. Yeah, everyone would do this. Is a violation to no arbitrage. So if there is a dominant strategy, in other words, then there is no arbitrage. If there is no dominant strategy, well then, this is a precondition, the precondition to have also no arbitrage as a special type of constellation. So let's explain this with an example. Suppose we have an investment, it's risky. We don't know what is the payoff tomorrow. That's always here when we talk about financial investment. It's not a risk-free investment like a saving account investment, it's a risky investment. And in this simple case, I assume there are two states of the world. Yeah? One is called omega 1 and the other is called omega 2. You can say in omega 1 the price goes up of the asset, in omega 2 the price goes down. So there are two states of the world. One is reflected by omega 1, and the other is reflected by omega 2. And now I set up two conditions a market must fulfill that there is no arbitrage. The first one is kind of common sense. The probability, and I call this probability Q, that we are in situation omega 1, plus the probability that we are in situation omega 2, what should be the sum of both probabilities? 1, because always the probability add up to 1, and Q omega 1 or Q omega 2 is a number between 0 and 1. So if the likelihood that we are in omega 1 is 0.6, then the probability that we are in omega 2 is 0.4. So this is the primary, an elementary assumption in a risky market. And now the second equation reflects the market pricing. So suppose this is a risky investment in a stock, and the stock price today, let's say, is $5. And if the price increases, suppose omega 1 price is going up, and omega 2 price is going down, and suppose we have a call option, then we always know the payoff of a call option at capital T, right? The payoff of a call option is always the price at the end minus the strike price. So it's a plus, yeah? This is the payoff of a call option. And now suppose if the price goes up, this payoff gives me 6 unit times the probability that the market really is in this area. And if the price goes down, the payoff, let's say, is 4 times the probability that we are down. And the today's price is 5. That is what I just assumed here. So this equation is telling us, well, the today's price is nothing else as the probability of the future outcome. The probability that we are in the up state plus the probability that we are in the down state. And in kind of average, we call this later on in expectation, this should be equal to the price today, the €5. The question is now, can we find a Q omega 1 and a Q omega 2, so a probability that matches these two equations? So can we find a Q1 omega 1 equal omega 2? That solves both equations. If we can find such a solution, well then we can say it is in line with the probability and it is in line with this kind of pricing equation. Well, in this case, it is not too difficult to see the solution. I think you...
would be 0.5.
Yeah, it would be half. Yeah, so we can say if Q omega 1, omega 2 is a half, then you see a half plus a half is 1. 6 times a half is 3. 4 times a half is 2. 3 plus 2 is 5. So in this case, we really find a Q omega 1 and Q omega 2. And if this is the case, when we find such probability measures, then we can say there is no arbitrage. And this goes back to the so-called first theorem, fundamental theorem in finance. So we have two fundamental theorems in finance. And the first theorem in finance basically states the following. If there is no arbitrage, so in short, no arbitrage, if and only if, yeah, that is equivalent to there exists such a probability measure. No arbitrage is equivalent existing, there exists a, and these probability measures have special names. They are not called probabilities. They are either called risk neutral probabilities, so this is one name we use for these Q, or they are called martingales, a martingale measure, and there's a third synonym. Some people call them equivalent probability measures. So these Q are in finance called either risk neutral probabilities. Some people call these measures martingale measures. And there's a martingale theory we will talk about next week. Or some people call them equivalent probability measures. And if these martingales exist, yeah, then we know the market has no arbitrage. If we can't find Q omega 1 and Q omega 2, well then, this is an indication there's arbitrage. This is the fundamental theorem 1 in finance.
As understood, the Q's, the probabilities are of this price going up and down, right? Correct?
In a simple way, yes.
How do you know what the probability of price going up and down?
Yeah, well, that is what we have to talk about. That's so I cannot. You will see this, yeah. Okay, over time. So for a second, just take granted, and in this case, we figured out if the probability is a half of up and down. In this market, it works out. Yeah. So we can solve the pricing equation, and it's in line with the assumption of probabilities, of mathematical probabilities. Yeah, but it's not just a mathematical probability, therefore we do not call it just a probability. It is also a measure that is linked to the pricing aspect, which is covered by the second equation, and therefore we give them these risk-neutral probabilities or martingale, and these probabilities, these Q, are very special. And in the end, the idea is the following. If we find these Q, if we have the martingale, then we can price any asset today. You know, the ultimate goal is to find the price of a call option or a put option today. If we find the martingale of my call or my put option, well, then I can immediately price it. I can immediately tell you the price of a call and put option if I know the corresponding martingale representation. And we will talk about martingale theory. Yeah? So don't worry if you cannot really see the point. You will see the point after we are digging deeper in all this respect. Just take it here. So I will not prove it here, far too complex. I will just state it here because I will come back many times on this aspect. No arbitrage is equivalent to the existence of risk-neutral probabilities or martingales. And what we will see, that the whole pricing is easy if we have these martingale measures. If we don't have these martingale measures, then we have arbitrage, and then pricing is very hard, almost impossible. I give you an example. Suppose we have an omega-3. Maybe I use there's a third state of the world. Price can go up a lot, price can go down, omega-2 a little bit, and omega-3 price can down really a lot. Yeah, so there's a third. Then obviously all the probability measures should add up to 1, and there should be a certain outcome in this omega-3 state of the world. I don't know, 7 or 1, 5, or it doesn't matter what we write. We can even say 1 is the outcome. Yeah, it's 1 times this. Yeah, but the question now is, well, can we find an omega 1, an omega 2, and an omega 3 to satisfy these two equations? No. There is a whole range of possibilities, and that covers the fundamental theorem 2 in finance. So there is a fundamental theorem 2, and this states no arbitrage plus what we call complete markets. I will tell you in a second. So if we have no arbitrage and if we have complete markets, that is equivalent if and only if these martingale measures are unique. So can I say martingale measure is unique? If we have no arbitrage, complete markets, then this is equivalent to say we have a unique martingale. Back for a second. If we have a market just based on omega 1 and omega 2, we find 2 measures. Both have probability a half. That means we have unique. Yeah, there's a unique omega 1, which is a half, and there's a unique omega 2, a half. We have martingale measures. They are unique. And therefore, in this first case, you can say this market is not only there's no arbitrage, it's also what we call a complete market. Now we add an omega 3. And if I make this in a nice way, I can create a situation that, well, we will find maybe some martingale measures, but they are not unique. Yeah? There's a range of possibilities. And if we have a range of possibilities, then still maybe if we find a Q omega 1, Q omega 2, and a Q omega 3, but they are not unique, then we still can say in this market there's no arbitrage, but the market is not complete. It's what we call incomplete markets. Yeah? And how can we prove that, or what is the requirement of a complete market? So if I go back to this initial problem, so we can write down this in matrix form, right? On the left-hand side, we have 1, 5, and that is equal to a matrix which is covering the output 1 and 1, and here 6 and 4, and then we have these 2 probability measures, Q omega 1 and Q omega 2. We ever find omega and Q omega 1 and omega 2 if we can solve this system of 2 equations in 2 unknowns. And this requires that this matrix A is invertible. We can find the inverse of this matrix. Then we can find an exact omega 1 and Q omega 2. So this matrix A, though the inverse of this matrix A must exist, or another way to test or to check this, the determinant of this matrix is non-zero. If the determinant of this matrix is non-zero, then the inverse exists. Then you can invert, then you will find unique measures, and then we know the market is complete. If we cannot invert this matrix, that would indicate an incomplete market. Yeah? And that if we have an incomplete market, well, then pricing is very difficult, and we can only find a range of prices. So Black-Scholes does only work for a situation of no arbitrage, complete markets. In incomplete markets, no pricing does really work. You can only define certain price ranges. I will tell you this next, these price ranges. So let me sum up. The point of arbitrage, we need the condition of no arbitrage. Actually, in financial markets, usually we have no arbitrage. You cannot make a risk-free profit. That's the first point. And we need this idea also in theory to price assets. The no arbitrage condition is a primary condition to do the whole pricing. Yeah? And pricing has to do to find these risk-neutral or probabilities or martingale measure, these omega Q1 and omega Q2 in a way.